This video, we have a lion running at constant speed toward a gazelle. So let's turn this into our reference frames here. Here's positive, here's negative. Maybe we can make this a 0 point if we want. So we have V0 equals negative. Here we have V0 equals 0. The gazelle standing still. After several seconds, the gazelle notices the lion and accelerates directly toward him. So the lion's moving this way, it's continuing to move this way to constant velocity, and we have acceleration in that direction, hoping to pass the lion and force him to reverse direction. As the gazelle accelerates toward and past the lion changes direction and accelerates in pursuit of the gazelle. So now we have, what's going to happen here is the velocity must decrease for the lion, and then the velocity must become 0, and then the velocity is going to have to be positive. So when we're talking about the acceleration, the direction of the acceleration is the direction you might imagine pushing this thing to happen. So constant velocity, no acceleration, no acceleration. But here we've got acceleration, and you can imagine pushing in that direction, so that's the direction of the acceleration. But for the lion to slow down, the lion also has to experience like it's being pushed in the positive direction. And of course, it's that same positive direction that allows him to accelerate after the gazelle. All right, so the lion eventually reached constant but different speeds. Constant but different speeds. Which one shows a reasonable representation of the velocities? All right, so this is kind of distorted. So whenever we look at the graph, the first thing we want to consider is the y-intercept, the initial conditions. So let's first look at this. The lion, as we've drawn it, has an initial velocity that is negative, and the gazelle is 0. So let's see what we've got here. We have this is the lion, has an initial velocity that's 0, initial velocity that's negative, and the gazelle has initial velocity of 0. So just on the y-intercepts alone, choice A is consistent. And if we look at choice B is also consistent. If we look at choice C, we have the lion with a positive initial velocity and the gazelle with a 0 velocity, which seems to be inconsistent. The lion here, we have a positive initial velocity, and the gazelle is 0, which also seems inconsistent. So it looks like we're down to 50-50 right off the bat just by looking at the initial conditions. All right, so we've got a velocity of 0, and it stays velocity of 0 for a while, right? After several seconds, the gazelle notices the lion and accelerates. So we're now going to look at the gazelle to stay at 0 for a while. It does here. And in this second one, you notice right off, it accelerates right away. It doesn't stay 0 for a while. So it looks like choice B is out right off the bat because it doesn't stay still for a while. And it looks like we've eliminated choices C and D already. Now the gazelle has positive acceleration and then travels at constant velocity. Let's see if that's what happens with the gazelle. It accelerates and it stays at a constant velocity. Looks like it's consistent. The lion is running at constant velocity, negative constant for a while, and then experiences positive acceleration. And acceleration is the slope, so we should have a positive slope. So negative for a while, then positive slope. Notice the velocity is negative, and then it goes to velocity equal to 0, and then the velocity is positive. That shows him slowing down to 0 and reversing direction and then traveling at constant velocity. So A is consistent all the way through, but notice we got to 50-50 just by looking at the y-intercepts. Next question, a graph, Oizerga. Our origin, right here like so, there's our 0. Y-axis, velocity in normal units. X-axis, time in normal units. So we will be able to read velocity and time off the graph. The slope, delta V over delta T, is the acceleration. And we can see the acceleration is constant and negative. And the area, V delta T, is the displacement. All right, so time T0 is at a position of 0.5 meters. So we'll set up our coordinate system. It's at a position of 0.5 meters. T0, 0.5, and that is x0. The students generate a graph of the chart's velocity as a function of time, as shown above. All right, so we show this thing. It has a positive, it's a velocity moving like so, but it's slowing down and eventually comes to a stop. And it comes to a stop right there at about 1.5 seconds. And then it has a negative velocity in the other direction, and the acceleration is the same. But notice this occurs for 1.5 seconds, and the acceleration in the other direction is 1.0 seconds. So however far, what that means, however far it got in the positive direction with this positive area, it is not going to reclaim it with the negative area. You can see that if we were going backward, this green area, A, or the yellow area, A, and B are equal and opposite and add up to 0. So it will still be positive from its starting point of 0.5 by that amount of area. The position. Now remember, the area is delta x. Delta x is x minus x0, so the position x is delta x plus xo. So we know the xo was 0.5. We're told that in the beginning. And the delta x is going to be this area. And then this area is 0.5 on this side. And the height, at 0.5 seconds, it's 2. And at 0 seconds, it's 3. So that means the average is 2.5. So we have a 2.5 height by a 0.5 width. So that area is going to be 2.5 times 0.5. And that's going to be 1.25. So we have an area, which is the displacement of 1.25 plus 0.5, which is 1.75 meters. Choice C. Number 18. An Oizerga again. Our origin, we'll double check here. 15, 10, 5, 0. That seems right. 1.5, 1.0, 0.50. So that's truly our 0 origin. Y-axis, velocity, meters per second, time in seconds, normal units. So therefore, we'll read the axes. Velocity and time. The slope is dividing the axes. Delta V over delta T is acceleration. And the area is V delta T. Meters per second, which is meters, and that is displacement. So we've got the velocity time graph. What best describes the motion of the object? Well, let's just see. The velocity is increasing, then travels at a constant speed, then slows down. Common misconception is someone might think this is going backwards. It's not going backwards. The displacement is the area. Notice I'm adding positive area. I'm adding positive area. I'm adding positive displacement. And I only stop adding positive displacement when the velocity gets to 0. So the entire time here, we are moving to the right in the positive direction. Acceleration, then constant speed, then slowing down back to 0. Is either speeding up or slowing down the entire time? Well, it's actually not true. It was at constant velocity some of the time. So that's out. The object starts and finishes at the same position. Well, if we're at the same position, the positive and the negative areas would balance out, but it's all positive area. It doesn't start and end at the same position. Same direction for the entire time. We think that's true. Positive area, positive displacement. It undergoes positive acceleration the entire time. Acceleration is the slope. This is positive slope. This is negative slope. So they don't have the same acceleration the entire time. And in fact, there's sometimes the acceleration is 0. Here, the acceleration is 0. So that choice is out again. Number 19, we do our Oizerga again. Here's our origin. And our y-axis is velocity in normal units, x-axis in time normal units. We can read the axes, velocity and time. Gradient is dividing the axes. Delta v over delta t is acceleration. Area is v delta t, which is meters per second times seconds, gives us meters. So the area is the displacement. All right, so here's our positive numbers. Here's our negative numbers. It's shown on the graph, which is true about the motion of the object. The object is not moving. Not moving means v equals 0 from time 4 to 10 seconds. So let's see, 2, 4, 6, 8, 10. From 4 to 10 seconds, at 4 the velocity is 8. No, that's false. The velocity is not 0. Initial and final positions are the same. That would mean that delta x must equal 0. And delta x is the area. So let's see, does the area, the positive area here, equal the negative area here? Now that might be possible. Let's see. Let's see what we have here. Let's break it up and figure it out. So we have this, which is a 4 by 10. So that's 40, and half of that is 20. And then here we have a 4 to 10, which is 6 by 10, which is 60. And here we have another 4 by 10, which is another 20. So this represents positive 100 meters. We could draw this rectangle, which is 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 by 5 is 90. So this has an area of 90. This has an area of 2. That's 2 wide, and this is 5. So that's 10, and half of that is 5. So 2 times 5 is 10. Half of that is 5. And we have the same thing over here. So 90 plus 5 is 100. So it looks like since this delta x is positive 100, and this delta x is minus 100, it looks like the final positions are the same. So it looks like this is the answer. Object is slowing down from 14 to 16. So that means the velocity must be decreasing from 14 to 16. Here's 12, 14. Well, the value is going from 0 to 5. It's actually speeding up. It's going from a velocity of 0 to 5. So it's not slowing down, it's speeding up. Acceleration from 0 to 4 seconds. Acceleration is the slope from 0 to 4 seconds. Slope is delta y over delta x. We have a change from 0 to 10 over 4 seconds is 2.5 meters per second squared. Is different from the acceleration 34 to 36. 32, 34, 36. Well, here we have a delta y of 5 over 2 seconds, which is 2.5 meters per second squared. And this one's positive, and this one's positive. So they actually have the same. There's a lot of work we do here to disprove all these. We want to be sure we don't miss a detail, but the answer is B. And our last question about our friends, the astronauts. So we have these two objects that are initially at rest. V0 equals 0, V0 equals 0. X throws a large container. So you see this container. It's going to throw it, and this one's going to catch it. Immediately after the container is thrown by X. Immediately after the container is thrown by X. So X has already thrown it after it's caught by Y. What describes the motion of astronaut Y in figures 1 and 2? Now, since we have these different bodies here, we have these two bodies here. There's a center of mass that's going on. Now, remember it says throws the container to Y. Shows the astronauts immediately after the container is thrown. So our system consists of astronaut X and astronaut Y. And we could assume for a moment the masses are equal. So that would make the center of mass right in the middle. That would make our center of mass right in the middle. And now our system consists of the astronaut, the other astronaut, and the canister. So what describes the motion of Y in figures 1 and 2? Question 20 is incorrectly labeled by the AP. This is not a kinematics question. So I apologize for that. This is not a question we can answer yet. It is not a kinematics question, so we'll omit that one.